In this section, we're going to start looking at polynomial functions and their graphs. So the first thing we have to do is define what a polynomial is. So you can read through this, but essentially, here's the things we need to know about a polynomial. A polynomial can only have real number exponents. They must be integers, and they must be non-negative. So really, we're just looking at whole number exponents, 0, 1, 2, 3, something like that. A 1/4 power makes it not a polynomial. A -2 power makes it not a polynomial, okay? And we've already talked about a little bit that the degree is going to be the highest power, and then the coefficient of the variable with the highest power is the leading coefficient. So here's some examples of things that are polynomial functions versus things that are not. So here's the two big issues you want to look for. If my variable has a square root, that means it has a fraction power, so that makes it not a polynomial. And if my variable is in the denominator, that makes it a negative power, so that makes it not a polynomial, okay? So that's what we want to be looking for. When we're looking at the graph, there's also some characteristics that are important about polynomials. Polynomials of degree 2 or higher are smooth, meaning that they're rounded, there's no sharp corners, and they are continuous, meaning that there's no breaks. You can trace the whole graph from left to right without lifting your pencil. So again, there's two graphs that are polynomials. The two on the right are not, because we either have to pick up our pencil to jump in the graph, or we have these sharp corners. That makes it not a polynomial. All right, we're going to review a couple of the things that we learned from Algebra 2. In Algebra 2, you looked at the end behavior of polynomials. End behavior, we can use the leading coefficient to determine what the arrows do on either side of a polynomial. So we're going to look at two things. Is the degree of the function even or odd? If it's even, the arrows are going to go if it's odd, the arrows are going to go opposite directions, odd, opposite. And if it's even, the arrows are going to go the same direction, either both up or both down. Then to decide which one of the two, it depends on whether the leading coefficient is positive or negative. So we can summarize what's in this box up here in the following way. If we kind of think about this as a table, we want to look at the leading coefficient, and we want to decide if it's either positive or if it's negative. And then we want to look at the degree, and we want to decide if it is even or if it's odd. If we have an even degree and a positive leading coefficient, think about like a parabola, squared, so it's even. A positive parabola opens up, and then a negative parabola opens down, so both arrows point down. If it is odd, think about a line. A line is to the first power, so that's odd. A line with a positive leading coefficient, which is the slope, is going to go down on the left and up on the right. And if it has a negative slope, it's going to be up on the left and down on the right. So that's how we can decide our end behavior. So let's look at a couple of examples here. Number 1, use the leading coefficient test to determine the end behavior of the graph of the function given. So for part A, we need to first make sure that this is in order so we can determine our leading term. And so the leading term is this right here. So the leading coefficient is 1, which is positive, and the degree is 3, which is odd. So we want positive and odd. You can look up at the table that we looked at before. Positive and odd means that we're going to be down on the left and up on the right. Now, when you're doing this in my math lab, the wording that they're typically going to use is, does it rise on the left or fall on the left? Rise on the right or fall on the right? So the choice you might see is this. it falls to the left, and it rises to the right. Now, another way we can say this, which we've seen before, is that we could use that infinity notation. So if that's the case, we would write it like this. On the left, we can say as x approaches negative infinity. So remember, we're thinking about a graph. Oops. Negative infinity on this side, positive infinity on this side. So as x is approaching negative infinity, so on the left-hand side, y is approaching negative infinity, the f of x. And then we could say for the right-hand side that as x approaches positive infinity, so as we move this way, y is also approaching positive infinity. It would be something like that. All of those ways of explaining it are going to be acceptable, but you might see like a multiple choice question written in all kinds of different ways. Okay, on B, it's a little bit tricky. We need to think about what the leading coefficient would be. It is not negative 4x cubed. Well, that's not the leading term, because we would have to think about what we would get if this was multiplied all out. This is not standard form. Because we only care about the first term, we don't need to multiply the whole thing, but we need to think here. We're going to have negative 4x cubed. When we square this, we're going to get an x squared. And this one here is just to the first power. If I multiply all of those things together, we get negative 4x to the 6th. So now we can see that the leading coefficient is negative and the degree is even. So that tells us that our arrows are going to be down, down. Or we could say it falls to the left, falls to the right, or as x approaches negative infinity, f of x approaches negative infinity, and so on. Okay, we're going to skip example 2 because I think it's kind of dumb. All right, let's talk about finding the zeros of polynomials. This is going to require factoring. So we've already talked about solving quadratic equations, how we can use the zero product property. With polynomials, it's the same thing. We're going to use our factoring strategies and set it equal to 0. So the zeros of a function are where f of x equals 0. Sometimes these are also called the roots or the solutions. Each root appears as an x-intercept of the graph. So really all 4 of these words tell you to do the same thing. Zeros, roots, solutions, x-intercepts. We all want to know what that gives us when we plug in 0 for f of x. So what we want to do is solve 0 equals x cubed plus 3x squared minus x minus 3. So the only strategy we have right now is to factor. Well, this one has 4 terms, so we want to try factoring by grouping. So we get x squared times x plus 3 minus 1 times x plus 3. That's going to factor to x plus 3, x squared minus 1. We want to factor completely, so I see a difference of squares there. So we get x plus 3 times x plus 1, x minus 1, and again, that's all equal to 0. So this is just like with the quadratic, except we've got 3 factors instead of 2. So the solutions that we get, where do these equal 0, would be negative 3, negative 1, or positive 1. Go ahead and pause the video and see if you can complete B on your own. So this is what you should get when you factor that out. And remember again that if you get a repeated factor, x minus 2, x minus 2, you need to write it using an exponent. That's going to be really important, and I'm about to tell you why. But so now we set each of these equal to 0, and we get x equals 0, because 0 squared would be 0, or 2. And even though that's squared, we don't need to write down 2 twice. If it's a solution once, it's a solution however many times. So that is what we get. Now here's why it's important to know the power of each factor, because it tells us about the multiplicity of the zeros. And this just gives us information about what the graph is going to look like. The number of times each factor appears, meaning its power, is called its multiplicity. So this is the one that we just looked at, okay? Each of these has a multiplicity of 2, because that's the exponent of the factor, okay? If I got an x cubed, it has a multiplicity of 3. If it was just an x, it has a multiplicity of 1, okay? So here's what's important that tells us about our x-intercepts. If r is some 0, so one of the solutions, and it comes from a factor with even multiplicity, then the graph touches the x-axis and turns around. I like to call that a bounce. It just bounces off of the x-axis. It touches it for a second, as you can see right here. It comes up and skims it and then bounces off and turns right back around, okay? If it has an odd multiplicity, then the graph is going to cross the x-axis, okay? So all we care about is whether it is even or odd. As the number gets bigger, it tends to flatten out near that 0. So for example, if I were to think about x cubed, like x to the first goes like this. X cubed flattens out a little bit. X to the 5th would get even flatter. X to the 7th would get even flatter. So that's what happens as the multiplicity gets higher, okay? So for example 3, we want to find the zeros. It's already factored, so that was very kind, and give the multiplicity of each 0. Then we want to decide what is the behavior at each of those zeros. So we can do this really quickly because it's already factored. If it wasn't factored, we'd have to do that first. So the zeros are going to be x equals -1, that's the first factor, and x equals positive 3/2. That comes from the second factor. Set them each equal to 0. The 1/2 does not have an x on it. That's just a constant, so we don't get a 0 from that. If it was 1/2 x, we would need to consider that, okay? All right, now what's the multiplicity of each of these? Well, this first factor is just to the first power. So this one has a multiplicity of 1, but this second factor is to the second power, so it has a multiplicity of 2. So what does that mean? 1 is odd, so that tells us that we're going to cross the x-axis at this point. 2 is even, so that tells us that we're going to bounce off of the x-axis. We're going to touch it and then turn around at x equals 3/2. Now, we don't know what the graph looks like necessarily. We could figure out the end behavior. It's going to be positive and odd. So it's going to do something like this. I have -1 and I have 3/2. My end behavior is going to be down on one side, up on the other. I don't know exactly what this graph looks like, but I do know now that at this 0, it's going to cross, and at this 0, it's going to bounce. So it has to touch it and turn around. That's what multiplicity tells us about the graph, okay? The last couple things that we want to look at today is the intermediate value theorem, which tells us about whether or not we are going to have a 0 or an x-intercept between two values.